Today I am going to present what is arch and why arch is preferable structure in the case of long span consideration, and what are the different types of arches. First look at this figure, this one. This is a simply supported beam, and here the load is present W per unit run on the simply supported beam. And this is the bending moment diagram of this simply supported beam. So at the midpoint, the bending moment is equal to WL square by 8. So figure 1 shows a simply supported beam supporting a uniformly distributed load. The maximum bending moment occurs at the center is WL square by 8. The maximum bending moment increases with the square of the span. Here you see the maximum bending moment increases with the square of the span. This is the span length L. The span length is your L, and this is the load W, and this is the maximum bending moment WL square by 8. So here the bending moment increases when the square of the span length increases. The maximum bending moment increases with the square of the span, and hence they become uneconomical for long span structure. So this is your beam structure. So long span length, the beam structure is your uneconomical, as the bending moment increases when the length of the span is increases. A larger section having maximum depth is also required at mid span. So at the bending moment is maximum at the mid span. Now you are clear. So because this is the simply supported beam, and due to this beam, so this is the bending moment, because the load is present on the beam is W per unit run, and the bending moment at the midpoint is WL square by 8. When the span length is increases, the bending moment is also increases. So because the maximum bending moment increases with the square of the span, and hence they become uneconomical for long span structure. So this type of structure is uneconomical. Resist the external load. Here you need the more depth section. Depth should be more at the mid section of the beam. That's why this structure is not preferable for the long span length. So what you have to do? So in such situation, the arch is preferable, and the arch could be used. In the case of long span structure, the arch is the preferable structure, so that you can use in more advantages. In such situation, arch could be used as they would develop horizontal reaction, which in turn reduce the design bending moment. So here you see, in the case of beam structure, there is no horizontal, because here this is the vertical reaction and this is the vertical reaction. But you see, this is the arch. This is your arch, and in the case of the arch is resting over the support, hinge support, and here this is the horizontal direction and this is the vertical direction. This is the horizontal direction and this is the vertical direction. The arch develop the horizontal direction, which in turn reduce the design bending moment. Due to the develop of this horizontal direction, here the bending moment is reduces. The bending moment in the arch is reduces. So what is the bending moment you will get at the section at any point in the beam structure, but in the arch you will get the reduced bending moment. Why you will get the reduced bending moment? Because due to this horizontal thrust or horizontal direction, the bending moment at the section is reduces. The reduction in bending moment resulted in section of smaller depth in comparison with the straight beam. So due to this reduction in the bending moment, the arch structure is more preferable than the beam structure in the case of larger span. In the case of larger span, so the arch structure is more preferable than the beam structure. And in the beam structure, so you need that the depth is more, but in the case of arch, you can provide the smaller depth of the section, and here the bending moment is reduces due to the horizontal reaction. So due to this horizontal reaction, you will get the less bending moment in the case of arch, and that's why you can provide the smaller depth in the case of arch structure. Look at this figure. here you see this is simply supported beam, and here this is the load is present at a distance L by 4 from the support A. So due to this load, what is the reaction at the end A? So this is your 3P by 4 at A, and what is the reaction at the end B? Vb is equal to P by 4. You know that is how to find out the reaction. And what is the bending moment at the loading point? So this is the load is present in the simply supported beam. So what is the bending moment here? What is the bending moment here? You know how to find out the bending moment. So bending moment, this is the reaction, and this is the distance. So what is the bending moment here? Va into L by 4. But Va is equal to 3P by 4. So 3P by 4 into L by 4. So the bending moment here is equal to 3PL by 16. So in the case of beam structure, if the load is present at a distance L by 4 from the support A, so the bending moment developed at the loading point is equal to 3PL by 16. This is the bending moment developed at the loading point. For example, in the case of simply supported beam with a concentrated load at a distance L by 4 from the support A, as shown in figure 3, the bending moment below the load is 3PL by 16. This is the bending moment developed at the loading point. In the case of arch, so look at this figure. In the case of beam, the length of the beam is your L. So the same length you take in the case of arch. But here you see this is the horizontal direction and this is the vertical direction. This is also horizontal direction and this is the vertical direction. The load is present at a distance L by 4 from the support A. This is the load is present in the arch. Here in the case of beam also, the load is present at a distance L by 4 from the support A. And here also you take the same span and the load is present at a distance L by 4 from the support A. Vertical height of the arch from the horizontal line is Y and the load is present at this point P here. So here you see in the case of beam, the maximum bending moment at the loading point is equal to 3PL by 16. But in the case of arch, what is the maximum bending moment at the loading point? Here you see, so this is the reaction. So due to this reaction, what is the bending moment here? Due to this reaction, that is the reaction at A, what is the bending moment here? Va into L by 4, but the reaction at A is your 3P by 4. 3P by 4 into L by 4. So this is your equal to 3PL by 16. So due to this vertical reaction, the bending moment here is your 3PL by 16. But what is the bending moment due to this horizontal reaction? So this is your equal to H into the perpendicular distance. The perpendicular distance is your Y, the H into Y. But when we are taking the moment about this point, so due to this vertical reaction, this is your rotating clockwise. And due to this horizontal direction, the moment, this is your rotating anti-clockwise direction. So take the clockwise moment is positive and anti-clockwise moment is negative. What is the bending moment at this point? So here the bending moment is equal to 3PL by 16 minus HY. So because due to this vertical direction, the bending moment is your 3PL by 16 and due to the horizontal direction, the bending moment is HY. But this is clockwise rotation and due to the horizontal direction, the moment is anti-clockwise. The bending moment below the load is 3PL by 16 minus HY. So now you compare what is the beam structure and what is the bending moment diagram. This is the bending moment in the case of beam structure below the loading, but in the case of arch below the load, this is the bending moment 3PL by 16 minus HY. So this is the decrease of the moment. So due to this horizontal reaction, the bending moment decreases in the case of arch structure. So you get the reduced bending moment in the case of arch structure. That's why this is more preferable structure when the long span consideration. In the case of long span structure, arch is the more preferable structure than the beam structure. It is clear that the bending moment below the load is reduced in the case of an arch as compared to a simply supported beam. It is observed that the cable takes the shape of the loading and this shape is known as the funicular shape. Look at these two figures. So this is one figure, this is the cable, and this is the arch. In the case of cable structure, this is the shape of the loading. And this shape is also known as the funicular shape. If an arch will constructed in an inverted funicular shape, then it would be subjected to only compression for those loadings for which its shape is inverted funicular. So this is the arch. So in arch, this is the compressive force at the support. So this is the compressive force. But in the case of cable, so at the support, this is the tensile force. And here, in the case of cable, the shape is your funicular shape. But in the case of arch, the shape is inverted funicular shape. This is the difference between the arch and the cable. Cable in tension and arch in compression. Always the arch is under compression and always the cable is under tension. Since in practice, the actual shape of the arch differs from the inverted funicular shape. Actually, the actual shape of the arch is differ from the inverted funicular shape. Arch are also subjected to bending moment in addition to compression. So the arch is always subjected to bending moment in addition to the compression, because here you see this is the horizontal direction. So due to this horizontal direction, the arch develop the compressive force. So this is the compression, this is under compression. In addition to the bending moment, so here also you have to take the compression. Arch are also subjected to bending moment in addition to compression. Arch is resist the compression and also resist the bending moment. As arch are subjected to compression, it must be designed to resist buckling. So always for any compressive force, you have to design the buckling. You have to consider the buckling design. Structure is classified as an arch not based on its shape, but the way it supports the lateral load. Arch support load primarily in compression. Arch support load primarily in compression here, in addition to the bending moment. For example, in beam, no horizontal direction is developed. You see that in the case of beam, there is no horizontal direction is developed. But in the case of arch, there is development of the horizontal reaction. For example, in beam, no horizontal direction is developed. Consequently, bending moment is not reduced. It is important to appreciate the point that the definition of an arch is a structural one, not geometrical. Here you see, this is one typical arch bridge, and this is the arch. This is the arch, and this is the span of the arch from this support to this support. This is the span length. This is your known as the span of the arch, and where the arch is resting, that is called the abutment. The topmost point of the arch is called the crown, and this point. So this is the bottommost point, and from this point, the load transfer from arch to abutment. Here, through this point, the load transfer from arch to abutments, and this is called the springing. The lowermost of the arch is called the springing points. So through this point, the load transfer to the abutments, and this is called the rise. This is called the rise. The height of the crown above support level is called the rise, because this is the support level of the arch. This is the support level, this is support, this is another support, and this is the horizontal line. So from this horizontal line to the crown, this height is called the rise. This height, that is the height between the support level and the crown. This height is called the rise. For large span structures like bridge, arch are provided instead of beams. Arch are chord beams. Arch are chord beams that transfer load to their planes. The load is transferred from springing to abutment. arch transfer load to abutments at the springing points. Hinge may be provided at the springing points. Hinge may be provided at the springing points. This is the hinge provided at the springing points, and through this point, the load transfer from arch to the abutments. The topmost point is called the crown. This is crown, and the height of the crown above the support level is called the rise. Due to chord nature of arch, they give rise to horizontal forces, because this is the arch is a chord structure. Arch is a chord structure. Due to the chord nature of arch, they give rise to horizontal forces. This is the abutment. The arch is resting over the abutment, and here develop the horizontal force and the vertical force. This is horizontal direction, and here this is the vertical reaction. The abutments are designed for horizontal force also. This is also designed for the horizontal force. What is the force you are acting here? What are the load transfer from the arch to the abutment? So by considering this load, you have to design the abutment for the horizontal force also. And you see at any section of an arch, let us take one section here. This is arch, and take one section here. So at any section in the arch, so here this is subjected to the normal thrust. The normal thrust is always perpendicular to the section. So this is the section, and here this is the normal thrust you are acting on the section, and here this is the radial shear you are acting on the section, and here the bending moment you are acting on the section. So here this is the arch, and here this is the section. So at any section in the arch, it is subjected to normal thrust, radial shear, and bending moment. Q is the radial shear, and N is the normal thrust, and M is the bending moment. Loads in the arch partly transferred by axial compression and partly by flexure. What is the load you are acting on the arch? The part of the load is transferred by axial compression, and part of the load is transferred by flexure. So loads in the arch partly transferred by axial compression and partly by flexure. This is types of arch. There are mainly three types of arch that are mainly used in practice. One is 3-hinge arch, 2-hinge arch, and fixed arch. These are the different types of arch, three types of arch. These are the three types of arch: 3-hinge arch, 2-hinge arch, and fixed arch. So this is 3-hinge arch. So in 3-hinge arch, so there is 3 hinges. So this is 1 hinge, this is 1 hinge, and this is 1 hinge. At 2 support, 2 hinge, and at the crown there is another hinge. And the reaction is develop horizontal direction at A and vertical direction at A, horizontal direction at B, and vertical direction at B. So there are 4 reaction components in the case of 3-hinge arch. So these 4 reaction components that you can find out from the static equilibrium equation. There is 3 static equilibrium equation. One is summation of vertical force is equal to 0, summation of horizontal force is equal to 0, and the summation of moment is equal to 0. 3 equation. But here there is 4 unknowns, 4 reaction components. So how will find out these 4 reaction components? Here you see the bending moment at the hinge is 0, because here in the case of 3-hinge arch there is 3 hinge. So 1 hinge is at the support A, and second hinge is at the support B, and the third hinge at the crown. So you have to take another equation. The bending moment at the hinge is equal to 0. You have to take the additional equation. The bending moment at the hinge is equal to 0. From the static equilibrium equation, you got 3 equations, and another additional equation you will get. The moment at the hinge is equal to 0. So you got the 4 equations. These 4 unknown reaction component that you can find out. 3-hinge arch is a statical determinate structure. This is, if the central hinge is present at the crown, then this type of arch is known as 3-hinge arch. 3 charge is statically determinate structure, and its reaction or internal forces are evaluated by static equilibrium equations. You know these three equations, summation of vertical force 0, summation of horizontal force 0, and summation of moment is equal to 0. The bending moment at the hinge and at the crown is 0. The bending moment at the hinge and at the crown is 0. So this provides an additional equation. As the bending moment at the crown or at the support is 0, so this provides the additional equation. So 3 static equilibrium equation, and this is the 4th equation. So using these 4 equations, you can find out what is the reaction VA, HA, VB, and SP. In 3 hinge arcs, there are 4 unknown reactions VA, HA, VB, and SP. 3 static equilibrium equation and 1 additional equation, that is 4 equations are sufficient to determine the reaction at each support. The main advantage is that it is insensitive to foundation settlements and change of temperature. This type of arch is preferable for wide span roof. This is less preferred in railway bridge because of the discontinuity at the crown and hinge. So this type of arch is generally less preferable in the case of railway bridge structure, because here this is hinge and this is at the crown, there is also one hinge. So due to this discontinuity, so this is less preferable structure in the case of railway bridge. Then this is 2 hinge arch. This is 2 hinge arch, and in 2 hinge arch, here you see there is no hinge at the crown. In 2 hinge arch, there is no hinge at the crown. The only 2 hinges is provided at the 2 support. There is 2 hinge at 2 supports. This is one support and this is another support. So this is one hinge and this is another hinge, but there is no hinge present at the crown. At the crown, there is no hinge. So here the horizontal reaction at A is your HA, and the vertical reaction at A is VA, and the horizontal reaction at B is SP, and the vertical reaction at B is VB. So these are the 4 reaction components. 2 hinge arch is a statically indeterminate structure. This is statically indeterminate structure. If the central hinge is not present in the arch and the member is made continuous between the supports, is known as 2 hinge arch. If the central hinge is not present in the arch, because here there is no central hinge. If the central hinge is not present in the arch and the member is made continuous between the supports, is known as 2 hinge arch. Here the member is continuous between the support, because this is one support and this is another support, and this is the structure is continuous over the 2 supports. So this type of arch is called 2 hinge arch. In 2 hinge arch, there are 4 unknown reaction components VA, HA, VB, and SP. But the available static equilibrium equation are 3, because you have 3 static equilibrium equation. The summation of vertical force is 0, summation of horizontal force is 0, and summation of moment is equal to 0. Hence it is called the statically indeterminate structure, because here there are 4 unknown reaction components, but the available static equilibrium equations are 3. So the degree of static indeterminacy is equal to 4 minus 3 is equal to 1. The redundant reaction H are determined by using strain energy principles or by the flexibility matrix method. What are the redundant reactions? You can find out using the strain energy principles or by flexibility matrix method. Then coming to fixed arch, this is known as fixed arch, or this is also called hingeless arch, because there is no hinge. Because this is one support and this is another support. Support A is fixed and support B is fixed. There is no hinge at support A and B. So here reaction produces at end A and B is the horizontal reaction at A, vertical reaction at A, and the moment at A. Similarly at B, the horizontal reaction at B, vertical reaction at B, and the moment at B. At each support, there are 3 reaction components. In the case of fixed arch, at each end, there are 3 reaction components. So at support A, the reaction component VA, HA, MA 3, and at B the reaction component is your VB, SP, and MB 3. So the total number of reaction components are 6. But how many static equilibrium equations are available? 3. So what is the degree of static indeterminacy? This is also the statical indeterminate structure. The fixed starch is also a statically indeterminate structure. Here the total reaction component is 6, but the available static equilibrium equation is 3. So the degree of static indeterminacy is equal to 6 minus 3 is equal to 3. If the supports are held in position and restrained in direction, then this type of arch is known as fixed arch. The deflection and rotation at the support is 0. The deflection and rotation, because there is no deflection at the support and there is no rotation at the support, because there is no displacement along the vertical direction, or there is no displacement along the horizontal direction, and there is no rotational displacement. There is also no rotational displacement. So the deflection and rotation at the support is 0 in the case of fixed arch. Fixed arch is also known as hingeless arch. The total number of unknown reactions are 6. 3 reactions at each support. They are vertical direction, horizontal direction, and fixed moment at each end. VA, HA, MA, VB, HP, MB. These are the 6 reaction components. It is statically indeterminate structure. The total number of unknown reactions is 6, and the available equations are 3. Then you can find out the degree of static indeterminacy of fixed arch is equal to 6 minus 3 is equal to 3. So this is all about the arch and types of arch. Now you are clear. So what is arch and what are the different types of arch?